Hey everyone, I'm back, and this is the second part of me explaining the gravitation topic. And this part has a lot of formulas. It might get a little confusing, especially because this is where I write all my formulas. I hope you're able to get it, and if not, again, comment me, reach me out somehow. I will explain it to you personally if you need help. I'm always here. Yeah, I'm not just helping you all, it's also helping me out. So I would love to help. Okay, anyways, gravitational fields. Okay, the region, it's gravitation, a gravitational field is defined as a region in which a test particle, an object, experiences an attractive field towards the center, the greater mass, the planet, whatever. Okay, so this field is basically spherical in shape. It has no boundaries, no defined boundaries. It has a virtual, what do you call it, a virtual boundary. We assume that it has a boundary, but in reality the gravitational field does not stop ending, but at one point it becomes so small, so insignificant, that it is basically non-existent. And at the point that it becomes that small, that non-existent, is called the end of the gravitational field. So yeah, so all gravitational field lines, all, you show every force with an arrow. So, and every force has a field around it in which it acts. So I don't know if I said that right, but still, I think you get the concept. How the area around it, an area around an object will attract all things towards itself. The force, so the force is actually acting towards the center. Okay, so what? Now we're going to talk about the line density of such areas. So let's see. So line density is basically the number of lines per unit length. And the more this density is, the higher, the stronger the field is. So basically, imagine this object, okay? My hand, this part is an object, and it has three lines over here, right? So at this point, let's say it's 1 meter, and at 1 meter, we have three lines over here, and they're diverging, okay? So over here, they're gonna be the strongest. But when we move up here, say perhaps, so this line over here is now out of the 1 meter boundary, and only two lines are within it. So over here it's two, so it's weaker. We have two lines, the density dropped from 3 to 2. We move even further up, the straight one is here, this one is the left one, is right one, whatever you see. The density drop even more. So yeah, so it's gonna be weaker. Moving on. So the field strength at a point in a field is defined as force exerted by source per unit mass for a test particle. It has a vector and is measured in Newton per kilogram. And it's not just, I know this is unprofessional to read and dictate what you're teaching, but this is a self-helping project. So I'm basically grooming myself too. So I hope you can excuse my little references to my notebook. Okay. So when an object is in a field, it exerts a force. It, not exert, it feels a force. It is affected by a force. So the strength of this force is basically the force acting per unit mass. So the more the mass, the more the force. And yeah, so basically we are the defining formula. I'm so sorry, I'm so confused. It's just I'm kind of sleepy, but around 3 a.m., 4 a.m. is the only time I get to properly make videos, because otherwise this door over here keeps opening, another door over here keeps opening. My brother's up, he keeps talking, my mom keeps shouting at me, and there's a whole lot of mess, a whole lot of fuss, not a mess, a fuss, just too much for me to concentrate and study and teach in silence and in peace. So again, so the formula here is G is equal to F upon M. Okay, G is equal to F upon M, but G is not directly proportional to 1 upon M, because this force right here um, is not a constant force. It is constantly changing and it depends on the mass M. Okay, so the gravitational field strength cannot be written as inversely proportional to mass. That, the lower the mass, the higher the gravity. That is wrong. Okay, first of all, we studied in part 1 that force of an object is G m1 m2 upon r square. Now m1 here can be a capital M, which denotes the mass of the earth, and the small m can be the mass of the object. So G mm upon r square replaces F, and F is upon M. So the M below the F gets cancelled out by the M of the F. So basically, we had G is equal to capital G M over R square upon M, right? Like this. I hope you guys can see. Um, yeah. So then this mass and this mass gets cut, and we're left with Gm upon R square. Over here, it's okay to say that G is inversely proportional to 1 upon R square, because both M and G are constants. So that seemed like a forced derivation, but it is. But it is also part of our syllabus, and we need to have a proper understanding of it, that G is not inversely proportional to M, it is inversely proportional to the square of the distance. Yeah. Okay, moving on. Now, this was for points above the surface, right? When you have a point mass and you have the. All right, I needed to discuss point masses. Okay, in this chapter, it's important to say point mass, because when we are talking about gravity, we are assuming that all the mass of the object is concentrated at one point in the center, because otherwise, when the mass is distributed, it's gonna have unequal attractions at different positions, and it just it creates a lot of fuss. So we're gonna call everything a point mass. The distance between 2 point masses, the mass, the product of 2 point masses, etc. Okay, so this was for objects above the surface of the planet. But what happens when we talk about objects below the surface of the planet now? I think I'm gonna have to explain it somehow. Just give me a moment here. I need to find something that I can maybe explain it with. Um, okay, I think I have an example here. So let's see. This is our planet, okay, and this is the object. When it's outside, when it's above the surface, say this is the surface, this is like this entire thickness is the planet, right? When it's above the surface, this whole thing is pulling this object towards it. But what if we drill a hole and we leave the object between these two, right? Like this. So now this part is going to attract this object over here, and this part is going to attract this object over here. And as the object goes deeper down towards this side, the mass on this side is going to increase, so the force that's pulling it towards this side is going to increase proportionally. So whenever we talk about objects below the surface, we say that the force that is exerted, the resultant force exerted on that object, because it's also being pulled to this side and this side, when we cancel it out, we get the result, and it is directly proportional to the distance of that object from the center. Because if one mass is reducing, the other is increasing at the same rate, it's directly proportional. Okay, so yeah, we got that out of the way. So now it's time to sketch out a plot and to derive a formula. So about the graph, actually, first we're going to go for the formula, so that once you know the derivation, you can physically see that they are directly proportional. So in our previous formula, we came to the conclusion that g, small g, is equal to the capital G, the gravitation universal gravitational constant, multiplied by the mass of the Earth upon r square, right? Like this. Ah, like this. Okay. Now we're gonna do capital G upon r square, and we're gonna isolate the mass of the Earth. All right. Now we know that density is mass upon volume. And when we make mass the subject, it becomes mass is equal to density into volume. So that's what we're going to do here. We're going to say G is equal to capital G upon R square multiplied by density into volume, right? Now, this is assuming that the density is constant, but in reality, it's not. At many points, in the Earth, in many locations, we have a hollow space. We have gas reserves, we have oil reserves, at some points we have metal ores. So the density keeps on changing, but for the sake of calculation, for the sake of sticking to our syllabus, and I could go out of the way, but it's basically countless, because I'm just teaching you guys for your exams and not for knowledge, even though I'd love to, and I should do it later on topics that I love. But anyways, back to this. We're gonna replace the volume with the volume for a sphere formula, which is 4 upon 3 pi r cube. So it becomes gravitational field strength is equal to universal gravitational constant capital G upon r square into density into 4 upon 3 pi r cube. Yeah. Okay, so these are the derivations that we've reached so far, and we're gonna cut this r square over here. Sorry, this r square over here, and we're gonna be left with just one r over here, right? So at this point, sorry again, we reach g is equal to g into density into 4 upon 3 into pi into r, like this, right? Now we know here that this is a constant, this density is a constant of the Earth, this number is a constant, and this pi is a constant. The only variable we're left with is r and g. So g is directly proportional to r. There you have a formula based reasoning. And if you know, directly proportional graphs are plotted by showing same lines, a straight line like this. Now this is gonna be our g, and this is gonna be r. Let's say this point here is the surface of the Earth, r. Now what happens after we escape the surface of the Earth? We read that g is inversely proportional to r squared. And we know that the formula for inverse proportions are drawn like this, right? A negative exponential curve, you could say. So over here, it's gonna start decreasing again, and it's gonna decrease till infinity. So at one point, we're just gonna show it parallel to this, what do you call it? Axis over here, the horizontal axis, right? Alright, so now that we got that figured out, all right, we do know that this was for G plotted against R. If you plot for G plotted against R square, and this is for lengths above the surface, the curve we draw is again gonna be a negative exponential, but not quite exponential. It's gonna be much steeper, like this. Yeah. Anyways, moving on. Now we know that this is this. Now we're going to talk about a few more graphs, and then we're going to talk about a few derivations for a center of the mass and all that stuff. Anyways, talking about the graphs, this is going to be R, and this is going to be R. And we're going to go like this, and okay, actually downwards. You guys are probably thinking I am a nutcase. Anyways, okay. Yes, I'm trying to fake my accent. What does it look like? I have to move next year. I need to start practicing. And hopefully, I get accepted because then it would be a shame. Whew, I hope I get accepted, and I hope I find a good university in Canada or UK. Cheap, good. I don't know. Okay, so we studied this graph here, right? Sorry, this one. Now, for quantities directed upwards as positive, downwards as positive, that if you're coming downwards, you're positive, then this graph is gonna look like this. Because if downwards is positive and you're going away from it, actually, I don't know if I should tell you right now, but this gravitational field strength over here is actually a negative quantity, and it has a permanent negative sign with it. So basically, when we're saying that downwards is for positive, and we know that this is a negative, so obviously upwards it's going to be shown upwards. And the reason it is negative, as I really shouldn't be telling you, it's for part 3, but I'm just going to give you a hint, is that you see our force is inversely proportional to r square, right? And at infinity, at the point where the field line, our field ends, we're gonna get f is equal to blah 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 upon infinity squared, and any quantity divided by infinity is zero. So all quantities below zero are obviously gonna be negative, right? Another reason is that, you see, repulsive forces, whenever we go against a force, we say that we work against this force, and so we gain a potential. Whenever we in an object, we used to study in O levels, that when an object is 3 meters above a particular surface, what is its potential energy? We say that it increased. So basically, we're going against a force. But when we're going towards it, when you're going from infinity to the center of the earth, it is obviously going to be negative because we're going with the force, not against it. I'm going to be talking about this in much more detail in part 3, and Hopefully, I'm able to talk about part 3 today. I wish I hadn't wasted time making a video, composing music, but I just needed a break. I needed to take my mind off of stuff. Oh, anyways, okay, that was that. Quantities directed downward, upwards is positive. Now we're saying that all quantities that went against the field were positive. Then this is obviously gonna be negative. Oh, I need sleep. I don't know what I'm saying. Just this is for directed downward as positive, and this is for directed upward as positive. And since it's negative, we directed it downwards. And I know I did not explain it that well, and I know I'm not well. So just comment if you think you need more explanation, or just try to reach me somewhere else if you have me added. And I'll try to explain and respond. Okay. Yeah. So now we're gonna go back to that old thing again about below the surface, an object being below the surface. And I'm just gonna show you these pictures over here. Okay, so like this. So you see this object here was this distance below the surface. So this object is being pulled by a force F1 directed upwards and force F2 directed downwards. So basically, we get a resultant force which is F2, which is the greater force, minus the smaller force. You see, and this resultant force um, actually we can also express this as just object of radius this much, like say of radius r from the center, that the planet pulling it. I don't think I'm well. I'm sorry, I didn't do you guys do, but I'm just gonna make this my last video for now and try to get some sleep. Yeah, I'm gonna do that. Okay, so basically, just I'm so sorry, guys. Just give me a minute. Maybe I can read it again and get a better explanation. Okay, I think I'm gonna end this here. This is not obviously not good for you guys. Me explaining like this. So this was incomplete. I'm left with like just one more concept and a summary of the form of all the formulas with explanations, and I'm hopefully gonna do it tomorrow. I cannot do it today. I'm so sorry. And I'm gonna do it with part 3, which is gravitational. I don't know. I'm just kind of blank right now. Okay, I hope you guys enjoyed. I'm sorry this video was not good enough. If you guys think that things were not clear, just please again leave a comment. I will explain it to you again, and if need be, I will make another video explaining everything from scratch. Okay, I'm just here for you guys. I am here to help, ready to help whenever you want it. Just communication is important, and if you guys communicate with me, you guys tell me what you need, you guys tell me what you don't get, obviously we're gonna have a better time understanding each other's problems and reaching a good solution. I don't know. Anyways, take care. I love you guys so much. Again, thank you for watching. If you did watch this far, it means a lot. Most people, almost everyone, never watches this far at all. Take care. I'm sorry again.